So then after that, there's an RZ, and this is going to be at 6.000, and then this is at Q2. And then the next one is basically another CX like this, and you'll see a lot of symmetry with this. So here to here, so Q1 to Q2, and then also another CX Q2 to Q3. So to Q3, okay? And another RZ, tab, negative 0.10, and then this is at qubit 3. So Q, and this is at 3. And then another CX. So you just see lots of symmetry here. So here's the CX. And after that's going to be a barrier. So I always double check. So I'm going to do this backwards. So CX, RZ, correct angle, or sorry, RX, CX. And then another CX, RZ. This is 6.0. And then you have this, basically, this looks correct. So, and I checked these kind of earlier. So I always make sure to enter, and then I'm going to go ahead and save. So enter, sometimes it'll always save, but to make sure to get the title, always click enter. So that's, unless you get a lot of, results that say, this is untitled kind of things. So that's saved. Everything looks right. The reset gates are in, measurements, barrier. And then I'm going to go ahead and set up and run. So on this specific one, it's going to run. And I could check the queue. So go here, go to jobs, and then see on this one, it says there's 10 ahead. So this will probably finish beforehand, which is good there. And then also, I wanted to show you something I've just kind of gotten started with. And it's in Quantum Lab. So on this specific one, it's called the Qiskit.circuit.library. So I'm going to zoom in. And it's a collection of well-studied and valuable circuits, directives, and gates. It's a learning curve, so you have to go through and say, for instance, these are some of the examples they get. So there, like I said, you can't do everything on the composer. You can't just create all the circuits in the world. Some just have restrictions, and there's just limitations to it. It's for basically for checking out smaller circuits, as you can see, like with the zoom. So if I go ahead and run this, so basically it's using MCX gate, setting it to qubit 5, and this is basically doing it inside of Quantum Lab instead of your composer. And you see the end qubit is the target qubit, which is 3. So you see Q3 is with the plus. And you can go on to IBM Qiskit and take a look at the library. Here's another one, Xgate. So this is basically, and again, it's a different language, or it's not readily apparent right away as far as this compared to OpenQASM. And there's just different things. So there's amplitude functions, adders, multipliers. It's basically the nuts and the bolts of creating quantum circuits the right way. And then you just have to basically abide by that. This is just how it is for that. So I'm going to save that. And then this is basically one of the main 3 sets that I've been working on. So this is Qiskit. This is the quantum evolutional neural network. What I like about this one is basically the only thing I had to fix is I had to get the JSON file from online, and then it's in the folder. So if I look here, this JSON wasn't on my particular one, but it's just easy to find. So you just right-click something, and then you're basically there. So I'm going to go through these, and basically these are all the things that it imports. You'll see for Optimizer, this is like basically training data. you know, you're talking images, those types of things. And then, so you have your 1 down, and then the second one I'm going to run, it's going to show this conv circuit. Now, the conv circuit is the basically the nuts and bolts to build the convolutional layer. So in this case, you see this, and it's 2 qubits, and then it'll get built up in the layer. So the next one is the conv layer, and then you'll see here that it uses this repeating pattern pretty much. It seems to change towards the end. So when it has this vertical line, it means that it continues on the next line. So you'll see the CX gates kind of get stretched between, you know, Q0 to Q1, and now it's Q0 to Q3. So it's very adjustable. I like this particular program because I can go in and I can just change this to an RX, or I can change this to a positive pi over 2. So there's many things to change with that. And it wasn't, I looked at this before and it wasn't inherently obvious, but this is the case, you know, that if you know a little bit about quantum, that it's kind of preferred there. Now, here's the pooling. So this specific one was the pool circuit. So when you have convolutional neural networks, you always have convolutional layers and pooling layers typically. And you can have additional things, you know, built on the ends of that. But basically, to build up that pooling layer, you can see that it, you know, it's increasing. Basically, it doubles in size to 4 qubits. So it seems like it's stretching some of these CX gates. And this particular one uses generate dataset. Now, generate dataset is it's a 2x4 image, and then if there's 2 yellows in a row, either horizontally or vertically, then that counts as a horizontal or vertical line. So this is the main parameters I was changing was generate data set and the test size equals. Now the test size equals in this case, it's 30% of 50. So the rest, the 60% is for training. So it's just, that's how the code is. It's just, you know, it's just a single adjustment that people can make as opposed to changing 50 to 30 or, you know, these types of things. So these are all in there. So yeah, 6 was run. And then, so what it's going to do now is basically, you know, it plots these and says, you know, this is horizontal, this is vertical, vertical, vertical. And then the next step is basically this Z feature map. And the Z feature map goes in front of the rest of the code. So you see there's Hadamard. So the gate colors are different from the composer. P gates, H, and then P. And then it's going to give a nice little representation. Now, this is the most accurate representation of what's going on. So sometimes when you zoom in, it gets smaller. Okay, so this continues. So this is 8 qubits. It's been built up from 2 qubit circuits that were, you know, originally coded, and you can change. And then you have the convolutional layer. This first one is 8 in the first pooling layer, and then it goes down to 4. So this is continuing from this line right here. So then you have this 4 qubits down to 2. Now, when you get down to 2 qubits, that's basically binary classification, and that's, you know, what a lot of people do. You know, there's you can have you could have many classifications to these specific ones. So just gonna, let's see here. So this next one, gonna enter, and this has to do with weights. So there's weights and biases. And this particular one is running quite well in the cloud. My Jupyter lab with the Penny Lane and other notebooks is kind of slowed down a little bit. I have to take a look at. But there's an advantage of doing all this in the cloud, right? So the hardware's in the cloud. You're not wasting your own electricity. And what this is basically, this is training. So again, with this. And this is based on the max iter. So max iter is set to 200. So you can see it's at 10 already. So it's like, you know, a 20th of the way done. So that has to do its own thing. And it's going to print out a specific case where it's, you know, it's going to print out the actual data with the horizontal lines and the vertical lines. They'll say, in this specific case, you know, basically it predicts a horizontal line. And if that's really the case, then it gains, there's 4 different images that it'll kind of pump out there. So I wanted to basically show, and I'll come back to the results. So remember, I ran that first circuit. This one on my screen, I can still see is running. And then I'm gonna, let's see, so the next one is basically this presentation. And let's see, so share. And then this should go to present. Okay, so this is basically, the outline for these demos. It kind of gets into some of the more details with it. And basically, I did a bunch of experiments, 21 of each. And the first one, again, is just vertical horizontal lines by IBM, running on a quantum simulator in the cloud. And I believe the training is being done quantumly, as you could see the qubits line up with those convolutional layers. And the second one, I think most of the training was done on my local laptop, this penny lane. And then, the quantum part was this small 4-qubit circuit for probably, it's a very limited thing that it does. Well, it's measurements and state preparation, which, on a quantum simulator, many papers are doing that. So, and the last one is basically inserting this brain data set. So as we can see here, so these are the comparison of these different networks. So the first two, and the second one I've kind of covered in previous ones, but just more thoroughly here, is that they're using hybrid quantum simulators. So that basically means quantum mechanics is run on a classical computer. And then the first one I really like because it's in the cloud, and from anywhere from my data is saved up there to, as things progress, I'm not having to upgrade this laptop, and you can get a fair amount of work done on an older laptop. The quantum simulator, on theirs, it ranged from like 7 to 8 gigabytes, and then these days 32 gigabytes of RAM, 8 cores. And then you'll see for the Xanadu, both theirs and mine, they ran theirs on, I think in 2021, are these default qubits, these simulators. Now the images tested, horizontal lines, MNIST data set. So the MNIST kind of gets the nod in that case. But again, I think most of the training has been done on the penny lane on classical. So, doing it quantum on a simulator, it's kind of like a relatively newer thing. So the image size, you could see that theirs was bigger in the penny lane. Now the training and testing on the published ones, 88.6 and 66.7 for IBM. And then for mine, I got 86.7, and then a testing of 100%. Now again, these aren't huge images, so it's, a 2 by 4, but it was the only 100% that I got, and I'll show you the parameters that I used for that. And then in specific, your Xanadu, your penny lane here, average test accuracy 49.2, not too hot. And then I was able to optimize that one up to 72%. And then my average test loss was less than their average test loss. So looking at the other ones, they optimized their own, cats and dogs, whatever data set they wanted to use. And I changed the parameters, the images, and then the split. So again, if you have 100 images and you have a 0.3 split test size, that's 30 images that are used for testing. And then the penny lane was more just enter in the values as you wish. And then I kind of optimized that to a training of 80. Now, as you can see, and I'm looking forward to programs like the IBM, because you can change the quantum gates. It's just right there in front of your face. Whereas with the penny lane, it's more like, I think the Keras and TensorFlow, that's doing the training classically, and it's basically have a smaller quantum circuit than the IBM. And then basically all of this is moving into having brain images, quantum computers. They'll still be hybrids, but basically trying to shift a lot of that work to the quantum computer, like the IBM is doing. More so than the penny lane is. And another cool trick that they do is they added noise. Now, this might affect results, but it's to simulate the real quantum computer, and basically so you don't have to, people aren't running nonstop on the real hardware. But that's another thing that IBM did, and to get 100%, based on that, it's a good sign that progress is made. And then basically some of the visualization stuff with the penny lane was, it looks good. And with this Python programming.net, I'm still looking at fixing some of these training errors that I'm getting. Now, this is the oversimplified version of the quantum convolutional neural net. And as you can see, this is 10 qubits. Now, what I showed you before with the code, it was up to 8. But this shows the new unitary functions, measurements, the final measurement, these types of things, kind of like how you'd normally see it compared to. And this is what we saw. And I actually, moved over the circuit, so it's just linear now, so it's not split. And this is the first layer, the second layer, and the third layer. Starting out with 8 qubits, essentially you're throwing out qubits along the way. Have the 2 qubits to get a binary optimization, i.e., is the image have a horizontal or vertical line? Now here's their data. So this top row is basically their data. So the 88.5% accuracy, and then for training, and then for testing, 66.67. And then at the bottom one, mine's 86.67. And then the way it works in the bottom right is it says the QCNN predicts this is a horizontal line. So whatever variables I gave it, it got the first image right. And then it says the second one is a horizontal line, which is correct. And then the bottom left was correct, and the bottom right. I don't know how it's distinguishing between, testing vertical and horizontal, but that was this number 6 run. Now I'll show you right here. So number 6 is basically 0.4 split off of 25 images, so it's smaller. And the iterations of 300 to get that 86.67 and 100%. Now I was able to get 100% accuracy on 2 of these with a 0.6 split, so more testing basically and less training. And then some of these, I got creative and I altered some of the circuits. So the comm circuit, the pooling circuit, and I just did 2 things in the pooling circuit, but I wasn't able to get great results with that. Again, more theory has to go into it as opposed to just changing something from pi over 2 to pi over 4, or having the CX circuit from 1 to 0 to 0 to 1, or having the pool circuit from pi over 2 to negative pi over 4. So this is basically, these are all of the smaller pieces that make up this IBM convolutional neural net. So you'll see in the first one is basically, this is the convolutional circuit. The second one is the layer. So the first makes the big one, or makes up the bigger one, or kind of the instructions for it. And you can see, so 961 out of 1024. The second one, 829 out of 1024. And this is likely because more gates, bigger circuits, more chances for things to go wrong. So you're not going to get as much of that single probability right there. And then you could see, going on to that next one is basically the pooling circuit. This is the smallest of the bunch. So out of 1024 shots, it had the highest amplitude of the probability of this, it's basically 7 zeros probability. I set theta equals to 0 because this can't technically be run. And it's, it basically seems to be, confirming that bigger circuits are more, are going to have more noise, and that's expected. And you'll see this last one. So smaller probability than the circuit that basically helped to define this particular one. Now, what's going to save the day with all this is basically better gate-based superconducting qubit like the IBM. Likely not better, we'll have small increases in quantum simulators, but there's issues with RAM and, just exponential amount of RAM, and that's where quantum comes in. So you want to run it on real quantum computers. And then also Quantinuum basically having their 15 qubits take less than 1.4 hours. So many applications, this isn't even close. If you want to do, simulations of drug molecules and caffeine and, the human receptors and those types of things is just not gonna cut the mustard having 25 qubits. But for imaging, you see some cooler stuff come through, and it's basically building quantum up, basically shifting it more towards the quantum code and then away from the classical code. And that's just it. This first option is what many papers have chosen. It's basically angle encoding, state preparation, and measurements. Now, the second option is basically, building circuits, designing algorithms that will fit, especially as quantum computers emerge with more qubits, less error. And you see, basically IQP kind of being this encoding method being a pivotal part. And I've seen other papers that I think they used IQP on a simulator, with some success, but then trying it on noisier hardware from, not too currently, not as much. So basically, and I've come across other presentations with this, and it's, larger kernel sizes is preferable, but if you do that classically, like the bare mathematics of it, you're exponentially increasing in time. Whereas with quantum, it's a logarithmic, similar to Shor's algorithm, that kind of theory. Now, to do this, there's been many awesome things said about quantum, and the biggest, most recent, it was last week, I believe, Cleveland Clinic and IBM, this healthcare and quantum computer, what effect will that have on the rest of the industry? And then also, we're waiting for the NSF practical quantum computer to be delivered. But there's a lot of people and a lot of funding put into quantum, figuring this stuff out. This is the penny lane network. Again, I'll show you the optimized training value. So on these specific ones, as you'll see, the penny lane's the top row, mine's the bottom row, and I just increased the training from 50 to 80 is what helped in that specific one. And there should be, okay. So this is basically that table. Now I've kind of learned some with the IBM as far as picking better variables to change, because a lot of these, these last three say just gave errors. And on this specific one, the only thing that seemed to really matter is end train and test. Number of epochs in theory may help, but if you see, and I'll show you in the next slide, if things are leveling out in accuracy, adding epochs, may not help. So I would say that's kind of the nutshell with this one is increased training. I tried increased testing, it didn't help as much. And then this kind of confirms that. So in a lot of these, if you look at like 15 epochs, it kind of levels out. So that's why it didn't seem to help too much if I bumped it up to 35 or 40, these types of things. And this is basically the set I was able to get the brain images into. So you download it from Kaggle, and then you're pointing your program to these files in that same folder. And then I can change it from 256 by 256 to 128 by 128 to 64. And I've seen AI, address these types of images that if you only want to take a single MRI scan and, it's pixelated like this on the right, and they get similar results than if you say maybe a 256 or 128. But there's certain things in learning that you can do to, basically have worse images and get that similar type of a result that you would if you had somebody sit in the MRI or lay in the MRI for a while. And this is a snip of the data set. So these are 512 by 512s. So I think it's like 160 megs, something like that, for 5,700 images. And there's other ones too. And this is just basically, and I've seen a similar, I've seen another paper use a similar types of data sets. And basically moving forward with all this with an MVP is, what are the strengths? What are the strengths of Qiskit? Most upgradable, for as far as that specific code, the hardware. And that's what I'm really liking is this cloud stuff. I'm not really into the Jupyter lab as far as, it's issues locally on the hard drive. And anyways, there's probably a way of doing that cloud too, but not out of the box. And its weakness is it's a basic, a 2x4 image, whereas the penny lane was an MNIST data set, but it was running, I believe, classically for the training, so it could handle it. So it's just bumping up quantum. So it's this natural evolution. using better and better hardware as it emerges. So, and you'll see the penny lane, good visualization. I could do FMNIS, which is fashion MNIS. I could do SciFar 10 a little bit. So that's kind of like a bump up. So SciFar 100 crashed on it, or I didn't get results on it. So the CNN is basically, these are established methods, and it probably comes with the dawn of deep learning. This is for imaging as far as when it became established. And the weakness to continue with this third one is I would have to re-engineer likely the whole software to address qubits, those types of things. So it would likely be an issue. Now, these top two I ran on real quantum computers. Now, they ran on quantum simulators, and these are the results I got. So on those specific ones, this IBM Nairobi, which is 7 qubits, I need additional analysis on that. And then these bottom two, I wasn't quite sure what the exact circuit they used for quantum was, because you could see this Kim Ryan. It didn't say how many layers. It's probably 6, because this paper came out in 23. That paper was 22, and then it was probably learning from that 22 paper. And then this bottom one is probably the most advanced, and the order, and it seemed like their quantum layer came before the convolutional neural net. It has these theta values, so it didn't quite fill out the chart, and I couldn't quite run it. So basically, for 4 qubit circuits, it's likely that they're using angle encoding, state measurement, state preparation measurement. The quantum algorithm assists the larger train test convolutional neural net. So again, it's just bumping quantum up. And this is the brain tumor one, so 95.6%. So they're getting bumps of using these smaller quantum circuits, but as far as them being the prime component to train and test, it doesn't look like it's quite there yet. And then on this specific one, so these are the splits of, these are all Alzheimer's ones. So I ran the first and the third one I showed in a previous slide, and these are the percents for reference. And you can see, so this is where everything's going, is basically this MVP is improving on current quantum literature, potentially using ion trap and IQP encoding moving forward. And then some of the building blocks for this, this first one, MPS meta ansets with two strongly entangling layers. Anytime you see that, like strongly entangling layers, that's usually like a sign that it's been optimized, for that. Now the second one, this is by Daniel Maheshwari. This is an encoding circuit with C0, RY, and RZ. And I learn something every time, or not every time, but like as you continue to learn these things, I'll learn different things from Qiskit. Now this last one is amplitude encoding. So these, if you look at just amplitude encoding circuits, they vary. Same thing with the IQP. And then here's the results on the right. So a lot of these are, running. And then, so this next one is an IQP. So this is Du, Y et al. Arrangement of quantum gates in a general IQP circuit. This next one, IQP, so this is a Strange Works Deloitte paper by Beloy, D et al. Last year. And this just gives you a frame of reference. And I had to modify some of these because I think it's a thing where you either need to find the gates and they're not readily apparent on Composer, this graphical interface, or find substitutes. But this is the modified part. This, basically, I think it's square root of x to the -1 I put in. But it's a shorter circuit, these angle encoding, where these other ones are longer, for IQP. And this is basically this isn't too out of date at this point. A lot of this is still up and running, but the INQ I showed with you is ARIA now. Quantinium, the H1-1 is the one I showed. And, Osprey, we haven't heard too much. And then Google, we heard there is an update from Google, is that they were able to get less error at higher qubits, which is promising. And then don't, discount spin qubits, photonics, neutral atom, and all these things. And this is basically more information to back that up. So there's a lot of focus and a lot of attention on quantum right now, and specifically getting not only the quantum computer to run better, but then the applications. Do you have your algorithm in hand? Basically when things get fixed. And this is basically, so this has been 30, so like basically 31 discussions on, medical research. And then also, this is literature, these types of things. And then also on quantum too, and kind of backing it up as far as, when all these quantum computers become available. And we're going to pop back to Qiskit. And then on this specific one, so let's see. So we're going to share this guy. So this is the finished results of, this is the IBM QCNN. And this is the accuracy. So I'll zoom in case you have a small screen. So 88.5%. This is training accuracy. So it says accuracy from the train data. So this was run. And then the other one is basically, it's going to pop out or it should, 86.67. So you see in this one, 1 is correct, 2 is correct, 3 is correct, 4 is correct. So there's more behind this. It's kind of interesting because this one looks 100%, but similar to this, where it doesn't quite make sense that I get 100%. And then anyways, there's more behind these types of things. And the other thing I want to show you is basically these jobs. So as you recall, so it's still in the queue. So that was half an hour ago, and its position is 12. If it's 6 hours, it's probably 20 or 30 minutes. That's not as relevant as this is. So anyway, that's up. That's in the queue. So it hasn't quite run yet on IBM's hardware. So I wanted to kind of get a take, and this is basically, so we're gonna, okay, so it should be able to, maybe we'll get more people in here too. So, okay, you should be able to come on now. So that specific circuit is still running. And then, hopefully you get a flavor of kind of what's out there as far as like, the penny lane locally or the Qiskit in the cloud. And I've heard from people, they say, I've run a bunch of experiments and I've never paid IBM. They don't have my credit card. So I know if you want the better hardware, more services, you have to start, paying them. But I know Microsoft, they take a credit card even before you start running anything. So it's just interesting. But yeah, Ron or Ryan? And you should be able to, and then if not, if you have any questions, you can put it in the chat as well too. So yeah, feel free to unmute yourselves, and then let me see if there's anything. What's it, March? And then I know for sure, so I know World Quantum Day is coming up next month, so that's April. So that'll be exciting. And let's see here. Go ahead, Ron.
Hey, Kevin. At the beginning, you were doing a quantum convolution, I think it was.
Yeah.
And I didn't quite catch it. Were you talking about how how the image was encoded onto the initial qubits at all?
Yeah, so for that one I searched, I don't know if it's IQP. So I searched for instantaneous and IQP, which would, both of those should work. And then, like most of the other ones I know are angle. And then I think the other one that's kind of popular is the amplitude. So it's either amplitude or, now what it looks like is basically is they try to just shrink everything down as far as image size so they could, get all of this adjusting, the circuits before they turn into layers kind of thing. So it wouldn't surprise me if it was IQP. And I've come across, basically they say that's the goal, is that's the only way that you really get, more full entanglement or exponential power and processing, those types of things. So like I said, I didn't find anything. I mean, to somebody with a more trained eye, they could probably look at it and say, oh, okay, based on this specific code, it's this means that. So I could pop it up here and then kind of checking that. So yeah, World Quantum Day is April 14th. So I remember that being a big thing in years past. So if I type in amplitude, it was actually, I would recommend it to anybody. I could post it in the chat here, this specific tutorial, because.
That was my next question. You got that code from a tutorial or a paper?
Yeah. And this one wasn't, say, as straightforward as the penny lane, but I kind of knew, because the penny lane up front, it just says enter how much training, testing, the batch size didn't seem to help much. But, it's just, after going through this for several weeks, I was able to kind of sift through, and I was like, oh, I really like this IBM one now, where when I first started looking at it, I couldn't make too much sense of it, where it's kind of light on the data set, but it's more heavy on the quantum. And I think it's, as far as it looks, because they put all the Qs with conv and pooling, that it's the convolutional part of this neural net is being done on qubits, as quantum simulators. So.
Yeah, and well, I thought it was quite interesting because you had popped up some graphics where it was attempting to show the images as a graphic of very large pixels. And I guess based on that, you can see that the size of the image is maybe 2 by 2 or 3 by 2 or 3 by 3. So that the issue with convolutions that are being used to, you had mentioned that if there's 2 pixels of the same color next to each other, that denotes a code or a graphical fragment. Actually, the way the convolutions work is they have to detect a threshold. So you're not looking for a specific pixel. You're looking for an edge, which means what it's looking for is the difference between 2 pixels. Now there might be a step in there where it calculates that difference and then colors them yellow. And then once you've done that, then you can move forward. But this is the first time I've seen something where there was a nice graphic that goes along with the results. So pretty cool.
Yeah, and like I said, there's more behind it, because say the axes on the training accuracy are not just accuracy. There's something else. And then if I look at mine compared to theirs, it's hard to tell. And especially for mine, that was 100% accuracy on 2 of my runs for train, that it wasn't quite apparent how it was getting that final value. So, but it seems like there's many ways, because the penny lane was more, you have these, it's based on epochs, and then you have a specific, test just test. And then you have a specific loss, as opposed to, I don't think I got a train value off that. But I think the most important is always going to be the testing accuracy, but you always want to check for overfitting too. And typically if you have low loss tests, if you had high accuracy for train, but low accuracy or loss, this is all loss. So if you have low loss for train, but you have high loss for test, that's a sign that it could be overfitting. And I haven't been able to see that yet, so that's good. And then I'm just keeping an eye out for this run. It's still saying 12. So if you get going, Ryan, if you have any questions too, is the queue time I've had say up to 2 months. Like if you run it on like a Sunday night when everybody else is running, it'll say, queue position 350, like 350 runs ahead of you. It'll say status queued 2 months, but it'll take less than 8 hours, that type of thing. So it's just, kind of figuring these things out, and they want IBMers for life, and they might get it. But if you can learn one language in quantum, the second one's not going to be as hard. So I would say I'm doing well in OpenChasm, but say, for instance, the Qiskit Python, which is in the lab, that's a little bit harder to master, because a lot of these things is you put in a specific, circuit from their library, and then their dots are different. So some is, angle, comma, whatever, and it's different for some other type of circuit. But again, with all these things, if you want to really master it, you have to do IBM lab, quantum lab. So the composer's only going to take you so far. It's not meant for everything. It can't do parameters. It doesn't know what it's pointing at, those types of things. So everything kind of has to be done in lab. And most publications, the images that they print are matplotlib, and that's typically done in lab. And you could do this in, Jupyter lab, notebooks, whatever. But yeah, I'm just sitting and watching. So I know there's time limits, and I think somebody said 10,000 seconds, and I think that's 3 hours. So it is possible, even if you have a queue of one person ahead of you, that you're waiting, for 3 hours because their experiment is just that long. Now, I will say this is basically with the Qiskit, the circuits running on real quantum hardware fast, is that I haven't had anything, I don't think, over 12 seconds runtime. And again, these are hybrid runtimes still. It's just you are using a real quantum computer at some point. So that doesn't seem to be the issue, because I've gone deeper up to, say, 6 or 7 qubits. And then I've gone, I've gone much deeper as far as like 6x layers. And then I've got it wider to 6 or 7 qubits. And like I said, it's usually 6 to 12 seconds, something like that. So that's not an issue. And, you kind of graduate, is you kind of learn these, and then you say, okay, definitively, I want to run this next, convince somebody, like, oh yeah, we should do this, and then bump up to a bigger quantum computer, an ion trap, or a better gate-based superconducting qubit. So. And then anything else as far as like, kind of the backgrounds there? I kind of know Ron, and then, coming from medical, coming from quantum, coming from, classical coding background, feel free to, you can come on or put in the chat. I will say this, it's easier to find Python groups, to learn Python, because, Qiskit's based on Python, than it is to find quantum computing groups. And you could probably find a good Python group almost every weekday. And some people like to do it on the weekends too. So those have been helpful. Go ahead, Ron.
If anybody wants a one-on-one Python tutor, I'm available. Pretty reasonable. I have taught Python as a CE course at a local junior college or community college. I also teach or tutor Bash scripting if you're into DevOps and want to master the command line.
Yeah.
I was going to say I had seen something that intrigued me on quantum convolutional networks and quantum image processing, and it sort of indicated that the real benefit for quantum, once even in the near term, where we just get a slight boost in scale, will be the ability to have a quantum algorithm slice vertically through multiple classical steps. So you're not necessarily processing the whole image, but a section of the image. You can do a convolution, you can do a scaling, you can do a pooling, all in one quantum process. So you're like piercing through the layers to give the ability to use quantum to like do multiple layers simultaneously, so to speak. Oh, it's not really simultaneously, but it's just like instead of having those separate layers that each have a specific classical image machine learning step, is you would have one quantum algorithm that kind of pierces through 3 or 4 of them.
Now that's interesting, because
yeah,
I would read up on, and this is me personally, there's certain types of nets. I don't know if it's, I think it is ResNet, and they kind of skip steps, you know, they'll skip a step. And instead of doing everything just like by the books of how you would normally do a conv and pooling layer. So that's interesting, because that could make things efficient.
Yeah, and I mean, if you think about it, because of the quantum's not scaling, it gives you the ability to, you might want, you might have, it may not be faster initially, but you can move the quantum viewport, you know, scan it over your image, and you can use a stride where there's no overlap if the quantum does what some of these people are saying it'll do. And the advantage should be that you're taking advantage of some of the quantum benefits of having the ability to amplify the right answers and to really knock down the bad answers, where that's something that classical just really doesn't have a handle on yet. And that's why these machine learning people get paid so well to come up with these techniques for massaging the hell out of the weights in each neural net layer. Again, if they get to the point where we can access a quantum computer that can do a 4x4, 5x5 or bigger, or some of the bigger scales, and then have the algorithm be able to just pierce through several of the classical layers, you know, you would get that speed up that way. But more importantly, like I was saying, quantum has this ability, you know, through the amplification algorithms to really pull out the good answers and really reject the bad ones. Still leave some stuff in the middle, but for a lot of different applications, I think it could be pretty cool.
Yeah, that's interesting, because, you know, a lot of people just don't know, or they might even discount, you know, these smaller angle encoding networks that's been used on at least, you know, 3 Alzheimer's, 1 brain tumor, a new breast. Well, actually, I don't know if that one has breast cancer. It's actually, it looks a little bit bigger than the other ones. And then at least 2 COVID, you know, that they're just using, you know, you have your conv layer, and then you have your you know, quantum variational circuit, 4 qubits, it always seems like. So, but yeah, I mean, that's the whole goal, right? Is to find out what doesn't really work well at all. Classically, takes an enormous amount of resources, has gotten lost in the dust, even because, you know, people just, you know, you assume that's just not something we've done, but maybe in the original article on convolutional neural nets, you're supposed to do that. You know, so I say it's interesting, it's exciting. So, you know, it's just, it always takes a lot of tests to figure stuff out. I thought that, so those four, so I ran a conv circuit, a conv layer, the pool circuit, and pool layer. And like I said, I had to set the theta equal to 0 on those. And then the results were kind of as expected. The bigger circuits had more noise. So your primary probability had less amplitude as the other ones. And that was, you know, that was interesting because that whole circuit, or that whole program I ran for IBM, that was on a quantum simulator, right? I don't know which one, because at the end they list a couple, but it was at least 8 qubits that it can handle. So I don't know what they're going up to, if it's like 30 or 50. I know it, and I'm assuming it's with the hardware. If you have awesome hardware, I've seen 50 qubits quantum simulators. So, and you could get a lot done. So they say the sweet spot, and I actually think it was Quantinium, maybe even the lady that came on to Anna's panel is, or actually it was probably Helen's panel, is basically that sweet spot is like 75 to 100, where we think, you know, quantum simulators, and they're slow anyway, but we think that they can't catch up to that point because it's getting to the point with RAM requirements, say past 50 to 51, I think it's exponential. So it'll be interesting, but I'm all for running whatever on, you know, whatever quantum system, and they say they've done over 2 trillion circuits. I think most of it's probably simulated. I'm all for running whatever gives the awesome results. And keep in mind, quantum simulators don't have error. So that specific one, the IBM that I ran, they actually add error into it, make it faulty, which I thought was interesting. So who knows, you could get closer to 100%, or actually 100% on every run, I don't know. And then, so anything else, any other questions or comments? So it could be anything kind of like programming, quantum, healthcare. Like I said, I think I got a big run ahead of me, so I don't think that's going to get finished today or during this call. Let's put it that way. I'd be interested if anybody went to APS physics in this month. Like I said, I think the World Quantum Day is more international. I don't think it's focused anywhere, but you know, it's just good to be a part of things. And it's been further simplified to me because I've studied many things in quantum and healthcare, and it's all about, that's really good, but then creating product, you know, is that next step. You could get lucky, you know, where it's not like taking months and months and months. But, you know, I join all these Python groups basically because it just gets my mind in that programming mode. And then I do YouTube videos, the 4-hour YouTube videos with Python programming. That might take me 8 hours because I have to stop and, you know, check my code and then rerun it. So it seemed to take forever. It was only 4 hours. So that was helpful too. And as they say in the startup world, you have to be the jack of all trades, master of none, meaning that you have to learn with the resources that are available to you. There's not a ton of, I would say, quantum is still relatively small compared to, you know, Python and, you know, the history of computing and this evolution of creating programs. But, you know, at that same time, you learn from Python, and then you're learning in Qiskit, and there are, you know, OpenCASM manuals. You know, this is the basic circuit composer in IBM. There's manuals on these things, but most people learn, you know, in bits and pieces.
Yeah, there's been some talk about putting together or pulling together a Qiskit, I don't know, learning group. I discovered that apparently there is a certified Qiskit developer certification, and supposedly, you know, all the material is on the Qiskit site somewhere.
Is it probably
So,
free too, isn't it, on IBM site?
well, the training materials is free. Somebody said that to take the test to get the certification is $200.
Oh, okay.
And that might mean it's done through a third party, so they don't, which I guess is smart on their part. But I guess we would be you know, some people might be like a study group, you know, so we like this is all up in the air at the moment, and there's you know, there's people out there, I mean, the Qiskit people have tons and tons of videos on YouTube where they talk about little pieces here and there, but I think the study group would be more more driven to just follow the documentation in whatever is there that they claim is that everything you need to know is in the Qiskit documentation, and you know, just go through it as fast as we can and see if we can you know, get up some confidence. And if somebody, you know, there might be a way to take the test for free. I don't know, apparently if IBM hands out tokens here and there, you might be able to get one to take the test. But
Yeah.
I think it could be, you know, even if you don't get the cert, I mean, it would be a good study group. So I'm just putting that out there. I don't know where it's going yet. If it'd be good to have a study group, but you know, I'll probably just dive into it independently anyways. So one way or the other.
You have to, in going to a bunch of these Python ones, you have to pick something, because we'll go through this thing called LEET code, LEET code. And it's
LEET code, yeah.
Yeah, it's like problems, you know, so you launch one or two problems. Now we got this calculator. I did a Python calculator tutorial that was more basic than what we saw. And, you know, we kind of chimed in as one person did it. Now this, and it may interest you, there's this thing called ensemble coding where one person does the typing, another person tells them whatever.
Well, that's called pair programming.
Yeah, para. Yeah. And I know that sounded interesting too, but in all these things,
those are really helpful, especially if you're new, and then hopefully you can get, like, some of them they'll put people together in groups of 4, and hopefully there, you know, at least one of the persons in the group has some experience with Python, and you know, even the experienced person will learn something because they'll learn how to be a mentor, if nothing else. But LEET code's one. There's a bunch of those out there where you can go and basically they got lists of what they call challenges, and there's one out there and I can't remember the name of it. It supports basically every language that's important, and it's like dozens and dozens of them.
And then, are we talking Kaggle at this point?
No, no. I have to go look up these other ones, but they're like LEET code, except they allow you to solve the problem in whatever language you want to do it in.
Yeah, I joined this Python one this morning, and it was basically to crack code, that kind of stuff. And there 2 of them were Microsoft, I think, engineers. The one lady, she has a PhD in quantum computing, which was kind of interesting. Wow. And they would be talking and trying to figure out the code, and it didn't seem like that, you know, it seemed like you need to just focus on the code. But
well, a lot of the challenges are directed at what are called dynamic programming concepts. You know, and the more experience you get with them, after a while, the challenges become easier and easier because you can see what they're trying to drive you at. I think Code Camp, something like Code Camp was one of them.
Yeah.
But there's been guys who started like they start a YouTube channel, and or a meetup channel, and through meetup they'll get you to come to their. It's like a Zoom call, except there's no video. Yeah. And then you basically, they have the ability to carve people up and put them into separate rooms. And then once you're in the room, you got, 4 to 6 people, and as a group, you have to solve the problem. Actually, another one was called Kikodo,
Yeah.
Kikodo. But
And
they
you know
have,
what this is leading to is basically a lot of these groups I go to is basically people trying to find jobs in coding. So Lead Code is known for a prep agent to get people prepared for their technical interviews. So when they go in and do these types of things.
yeah,
So, and I'm perfectly fine with that because that's the direction I'm heading to as far as like, organized and structure. It's, you get this specific program done and all these other things happen and testing and validation and when you get into medical now that's not even the biggest thing in medical. The biggest thing is patient safety, efficacy, these types of things. So yeah, I think that's what it is if people have jobs in Python, but some of the groups people do come that they have jobs, they're full-time programmers and they're just happy to learn more kind of thing. I was part of one, and one of the gentlemen, I sent him the link and he figured out that IBM QCNN while we were on the call, and he got a better training accuracy than I did, but then I modified more and then I got 100% testing accuracy. So it was kind of interesting because
yeah, there'll probably be some clever people popping up a site to do the same, do the lead code stuff, but only for quantum.
Yeah, because I would put people into kind of two camps as far as they really want to learn something new or they're satisfied with exactly what they have. Because they'll hear good things about quantum, but at that same time, it's just like, they are in that position of really wanting to learn something new, applying it, getting great results, or I shouldn't say great results at this time, getting different results, with quantum. So I guess to each their own, but I would say more often than not, it's harder to find a Python programmer that is excited about quantum because they'll just hear one thing and their brain will shut off and they'll assume that the problem in your code has to do with quantum computing. And then you'll find that one person, like I said, and this gentleman, he, installed the JSON file, put it in there, ran the code, liked it, thought it was interesting. You probably saw the qubits and all that kind of stuff, but it's news and it's different. And sometimes people in different stages of their life just aren't really ready for something new or want to, like that desire. But yeah, all very interesting. I appreciate the feedback. And then, so this has been episode 76, March 30th, 2023. Appreciate all the comments and suggestions. Looking forward to more emerging quantum hardware. Have a good rest of your night and have a productive rest of your week. Take care, everybody. Thanks for coming.
Thanks, Kevin.